a class focused on formal or deductive logic, we are doing the same thing there. Because basically, mathematically based sciences are deductive systems. They are closed systems in which you have articulated your fundamental truths, and all other mathematical truths are derivable from those foundational truths. The beauty of this is, ladies and gentlemen, is you can have what according to Descartes, as long as you don't screw up. The beauty is you can have systemic certainty. This is why so many of us, when we think of things that are true, we say, well, if there are absolute truths in the world, it can be found in things like mathematics and the mathematically based sciences. And I want to belabor this point just a little bit further with something extremely basic, just to give you the gist of what we're talking about. And this might give you flashbacks to an earlier conversation about Plato and or the Pythagoreans. If we have a line segment like so, folks, and we have this line segment like so right here, and if I tell you that this angle right here is x degrees, you can tell me without any hesitation and for certain that if this is x degrees, this must be 180 minus x, because the concept of that line segment is that line segment will encompass 180 degrees. And that's not a matter of what? It's not a matter of opinion. Now, admittedly, if we used a different scale, the numbers would be different, but the concept wouldn't be what? Wouldn't be any different. Let's say that we decided to call this 360 degrees instead of 180 degrees. Let's say we cut each degree in half, and a circle was 720 degrees rather than 360. The numbers would change, but the fundamental conceptualization would not. Do you get my drift? Now, of course, if I know this is 180 minus x, I know this must be x, this must be 180 minus x. This is just a rough and ready way that we can establish that corollary of what? What we call complementary angles. Now, of course, these are things that follow necessarily from the concepts that we already know. It didn't make a lot of sense to my 9th grade mind when I took the course. And that's because I was trained to be educated how? Meaningless rote memorization. Oh, if we had only been taught to think about things conceptually, think of how much wasted time would not have been futile. How many of you can relate? This is why some of us think, basic sort of philosophical concepts ought to be taught to middle schoolers. Because then we would have a lot more conceptual understanding rather than just rote memorization of things that you'll just what anyway? Yeah, you'll just forget them anyway. And by the way, I hated this stuff when I did it because I honestly didn't understand it. I just, mimicked what somebody else did. Things are a heck of a lot more enjoyable and interesting when understanding is involved. But yeah, this is what we mean by a coherence theory of truth. All of our mathematically based sciences are grounded in this model. This is why, this conceptualization of truth matters so much. Even though his meditations sound a little out there, this is the direction it's supposed to conceptually take us to. Now, one other thing I wanted to mention about coherence theories of truth, although it goes beyond the textbook. And this is what some 20th century critics have remarked about it. What happens, ladies and gentlemen, if one of your foundational truths is found at some point down the line to be flawed? What if one of our foundational truths it poses a problem potentially to the what? To the entire system. If we find a flaw in the foundations of a system of truth, it could pose a problem to the entire system. Because you know how the metaphor works. If you knock a brick out of the foundation, it might not knock down the whole house. But if a little more pressure gets applied to it, it just might. How do you think that a proponent of a particular system of truth might deal with a problem if a flaw is found in one of the foundational truths? Now, I'll give you a little hint here. This doesn't just deal with philosophy of science. It will deal with a theory of truth that we will discuss very late in the semester called the pragmatic model of truth. Mr. Gaskins.
I would say possibly hide it.
Yeah, well, we won't want to hide it because eventually that also means hiding it from ourselves. And if we really care about the truth, we would like our system to be actually one that can generate truth. So we're not going to hide it with BS. However, the answer I'm going to give might sound a little bit like it. Mr. Toberman.
Well, we restart from the beginning.
Yeah, there's two options. One of them is we may have to chuck it. Now, admittedly, this doesn't happen very often. Because to actually chuck a system of truth basically means to throw everything out. More often than not, we don't end up throwing out the proverbial baby with the bathwater. This is what we usually do. And this is the phrase that you will hear philosophers: ad hoc revisions. In other words, after the fact, for the purposes of making the theory viable again, we will revise our theory in order to accommodate anomalies. In other words, we will make revisions that will enable us to save the theory. Because this alternative is typically an untenable one. And I'm going to drop a name for you. I'll mention him later on. Philosopher and historian of science Thomas Kuhn. And by the way, if you think I'm needlessly name-dropping, I'm really not. Thomas Kuhn's book on the structure of scientific revolutions is considered one of the 100 most important books of the 20th century by the Modern Library Association. It has been conceptually very influential and well worth reading. Now, according to Thomas Kuhn, if we're not able to save a theory this way, through revisions, exactly what Mr. Toberman is talking about would end up happening. And if this happens, we would have what Thomas Kuhn calls a scientific revolution. Yeah, well, thank you. Scientific revolutions do not happen very often. As a matter of fact, the last major revolution in physics happened in the early 20th century, but it wasn't a complete revolution because we were able to make some revisions to keep what? Yeah, well, I say to keep Newtonian physics intact. Whose pioneering work that was originally panned, but then later it was uncovered that his concepts were extremely powerful. Yeah.
Was it Tesla?
Well, the answer to this one's Einstein. Einstein's general theory of relativity. It potentially could have led to a bigger scientific revolution than it did. However, the way that things ended up changing runs something like this. We still use Newtonian physics to deal with what kind of situations? What we would call everyday physical mechanics. When we're talking about relatively large things moving at relatively slow speeds. However, Newton's theories, or not Newton's, excuse me, Einstein's theories are applied when? With very small things moving at very high rates of speed. By high rates of speed, I'm talking about what? Speed of light. Your Ferrari doing 185, or whatever your Ferrari, or that's a Maserati, I guess. Yeah, your Maserati that does 185 is going slowly in Einsteinian terms. Of course, to our terms, 185 miles an hour is fast, but it's nowhere near what? Yeah, it's nowhere near the speed of light. Things behave normally, that is, in a Newtonian sense, at those speeds. It is at very high rates of speed, approaching the speed of light, that quantum mechanics applies. Now, of course, there's some people who believe that at some point, this entire system might fall apart. That is, if our elegant universe friends, we're talking about string theory and other models of physics, end up doing the job better than previous models do. But you'll notice that this is sort of a very last resort. More often than not, we will revise our theories in order to accommodate and keep the entire system of truth intact. Now on Friday, we will be discussing Descartes' meditations and the very bizarre conclusions he draws. Cheers.